One is you have drawn 7 line here, that is correct, but you have drawn 2 line here. So what this 2 line means?
Oh no, I just want it to be array, but I drew it.
See how you make it is like,
So I could just draw it one.
you just make it like this is the first thing and then this is the second, then in middle you are drawing like this. So this is wrong. Basically what you have to draw is only single line is coming. This is the white light or the sunlight. It got deviated here, it changes its angle, and this line only, from this line only you have to make it like this.
All right.
Okay, either you can make it from here also, like this also, or from here also you can show from this line, but from here you have to show only one line. Just open the WhatsApp if you have, just check the question I have sent you, this one, check. In the question paper, sometimes in the question paper itself you have the answer. In some another question you will get the answer of the another question. So go through that very carefully. On that same day, I have given you one question in which the diagram of the prism in which the dispersion is shown is given. I have already given it to you. But on that question, you are more concentrated on solving the answer, the questions. But you haven't noticed how it make the diagram. Okay, so this type of question will be there. You have to show how the dispersion is happening, how the light. The question will be perhaps like, what happens if white light passes through the prism? Draw the diagram and explain why white light is deviated the most. It will be for 5 marks. Okay, so you have to first explain why this person is happening, then you have to draw the diagram, then you have to explain the reason for it.
Okay, I'm just gonna fix it. Just give me a minute.
Pardon, I can't hear you. What you have said?
I'm just gonna fix my drawing, so give me a minute.
Okay.
Okay, I'm done.
Okay. So we'll start new chapter, sound. Okay, when I say sound waves, what comes in your mind? Sound waves.
Frequencies that we can hear.
Okay, so sound waves are basically those waves which can make a sensation in our ear, which we can hear. Okay, that create a sound. So now write down the heading sound waves. Under this, write down first heading origin, and transmission of sound. Origin and transmission of sound. Write down. Write down. In first bullet, sources of sound. Sources of sound all have sources of sound all have some part that vibrate, all have that part that vibrate. For example, a guitar has strings. A guitar has a string, comma, a drum has stretched A drum has a stretched skin and human voice has vocal cord. Human voice has vocal cord. Next bullet. The sound travels through the air. The sound travels through the air to our ears, and we hear it. Next, that the air is necessary for the sound to travel. Evidently, sound cannot travel in a vacuum. Sound cannot travel in a vacuum. But light can. Other material including solids and liquids. Transmit sound. Written?
Yes.
Mark this point as important. Last one. Now see what we have studying now. We are studying the origin of sound and how the sound is getting transmitted. So in that, first of all, you just understand that whenever there is a sound wave generation, whenever the sound wave is getting generated, so there will be definitely some vibration will be going on. Okay, whenever there is some vibration kind of thing, then only the sound can travel. Like for example, we have given 2-3 examples. Like for first example, we have taken the example of guitar. You have seen guitar. Guitar has thin strings, in which when we pull it from our fingers, so it make vibration, and through that vibration we can hear the sound. Clear? So that means what? That means there is a vibration. For drum also, drum is what? In drum there is a stretched skin. That skin, when we just push that drum, when we beat that drum, so what happened? That skin go up and down slightly. So that means definitely there is some vibration. That is why the sound is caused. Similarly, in human being, we have the vocal cords. When we speak something, that vocal cord, there is slight vibration. Due to that vibration, we can speak or we can create a sound through our mouth. And wherever there is a vibration involved, that means that sound will be generated. So what is the root cause of sound? How the sound is generated? So the sound is generated through the vibration. Clear? This point is clear?
Yes.
So the question can be asked in any way. You have to answer. What is the basic reason for the generation of sound? What is the cause of sound? What is the origin of sound? So every time you have to write the thing that the main cause of the main cause of sound wave to get originated is the vibration. And then you can give 2-3 examples. Sometime 4 options will be given to you, and in that you have to tell that where the sound will be generated. So how can you judge? You can judge by seeing that whether there is a vibration involved or not. If there is vibration, that means there will be sound generation. Okay. Now, next most important point is how the sound is transmitted. So in last chapter, I think last to last chapter, I have explained that the speed of light is 3 into 10 to the power 8 meter per second, and the speed of sound is 330 meter per second in air. Now, this light can travel with or without any medium involved. Whether the medium is present for the transmission, that whether it is we are transmitting light through air, or air is a medium, or suppose we are sending light through the vacuum. Now vacuum don't have any medium. Vacuum is a complete empty space. So either there is a medium or either there is a no medium, but light can travel. Like suppose we have created a vacuum here. This is what? This is vacuum. Now vacuum is nothing but the empty space. There is nothing in between. There is no atom, no molecule, no solid, no liquid, nothing. Empty space, complete empty. Now when we send light waves, so what happens? This light wave can travel through it with the speed of. But if we send sound wave, what happens?
The sound wave won't travel in a vacuum because it's all about vibrations, and since there aren't any particles to vibrate, it won't be able to pass through.
Correct, very good. So wherever the sound wave, we have the sound wave, so we require a medium for it so that the sound wave can transmit it. If there is no medium, that means there will be no transmission of sound. Clear?
Clear.
Now next heading, write down. Don't give heading. First write down in bullets only. So basically, the in exam the question will be like sound can travel through. For example, will be given. So you have to choose the thing. Okay, or that means the question will be like sound cannot travel through, so it will be vacuum. Solid, liquid, gas, and one option will be vacuum. So sound cannot travel through vacuum. So difference also clear between light wave and sound wave.
Yes.
Next, write down. Next bullet. Sound also gives interference. Sound also give interference and diffraction. Interference and diffraction effect. Because of this, sorry,
What's after diffraction?
effect.
Okay.
Because of this and its other properties we believe that it is a form of energy. It's a form of energy which travel as a progressive wave due to progressive wave which travel as a progressive wave, but is a type of longitudinal wave. Written?
Yes.
Now can you tell me what is longitudinal wave?
A longitudinal wave is a wave which the particles, the oscillation travels parallel to the direction of the wave.
Correct, very good. Now, what you have written, so sound can have the interference as well as diffraction effect. Now, very brief overview I'll give you for the interference and diffraction thing. So, interference is nothing but, suppose we have two waves. So, it is like the addition of the wave. Superposition of wave is the original word, but As if for now, just understand it's the addition of two kind of wave, and when we add the thing, so what happens? It will give you the increase in amplitude. So it is this kind of thing is interference. And diffraction is like, suppose some obstacle comes in between the path of the wave. So what happens? Suppose this is the wave, and here is some obstacle happening. So this wave can got dispersed. So this kind of effect is dispersion, this diffraction. It is like the dispersion thing. In dispersion, what happens? One sunlight is coming, white light is coming, and it got dispersed out. Similarly, in diffraction, what happens? Whenever some obstacle come in the path of wave, the wave got dispersed or it got diffracted from its original path. So this kind of effect is shown by the sound wave. So due to this reason, what we can consider the sound wave is a form of energy. You know, we can say sound energy, noise energy, that like this thing. So how we can say that sound is a kind of energy? So since it shows the interference and diffraction effect, we can say that it's a form of energy. Yeah. Now,
Okay.
we can also say that it's a progressive wave. What do you mean by progressive wave?
It would keep going, even like if you give sound, it will keep going on and on until it's not diffused, until it spreads out that you can't hear it anymore.
Correct. So basically, progressive, from the word itself, it is very much clear. Progressive means what? Progress will be going on. That means it will be definitely moving, and it will be moving ahead. Okay, so it's a kind of progressive wave. So progressive can be either longitudinal or transverse. So here the sound wave is the example of longitudinal wave. Now keep heading longitudinal wave. Now we'll understand how it is a longitudinal wave. Write down. Subheading, write down A, waves on a spring. Waves on a spring. Wave on a spring. First bullet, write down. In a progressive longitudinal wave, the particles of the transmitting medium, vibrate to and fro in the same line in which the wave is traveling, and not at right angles to it as in a transverse wave. The longitude, next bullet.
Just a second.
Want me to repeat?
No, it's fine. Okay, got it.
Change the paragraph or change the bullet. A longitudinal wave can be sent. A longitudinal wave can be sent along a spring, comma, stretched out on the bench, and fixed at one end.
Stretched out on what?
On the bench, table. bench, and fixed at one end. Fixed at one end, comma, if the free end is repeatedly pushed and pulled sharply, as shown in figure, comma, compressions, see the spelling on the screen, compressions in bracket C, comma, where
If you're writing anything on the board, I think you're still presenting the one from the light waves.
I have written compression in the screen. Can you see it?
No, I can only see the triangle you drew in the beginning of the lesson.
Okay. Just wait a second.
Okay.
Now can you see?
Yes, I can.
Compression C, where, first write down the spelling compressions. Written.
Yes.
Compression. Now what do you mean by compression? If it's a coil, like suppose this is the coil. So what does it compression means?
Pushed together.
Correct. So write down, comma, where the coils are closer together. Where the coils are closer together. And rarefaction. See the spelling. And rarefactions, capital R. Now, what is the meaning of rarefaction?
I don't know.
Rarefaction is the opposite of compression. Like suppose we have this coil, so compression will be like this. When it come closer, and rarefaction will be when it will move apart. It will be like this.
Oh, okay.
Okay. So write down where the coils move apart. Where the coil moves apart. And travel along the spring. Now, do you have your mobile with you? Do you have your WhatsApp? I'm sending a picture that you have to draw in your copy.
Yes, I do. Just give me a second. Okay. It's with me.
Yeah?
My phone's with me. Just whenever you got the picture, send it to me.
Got the picture?
Yes, I did.
Okay, draw it. Once you're done, let me know.
Okay, I'm done.
Okay, so basically what we have written, so we are discussing how we can say that the sound is longitudinal wave. So what do you mean by longitudinal wave? What is longitudinal wave?
The oscillation is parallel to the direction of the wave.
Correct. So I said that when I was teaching you longitudinal, so I used the term to and fro motion. To and fro motion. And when I was teaching you transverse, so I used the word up and down. Remember?
Yes.
So to and fro means like this. So this we can say from the an example of spring. You have to just fix the spring in one end of the table or bench or wherever. Fix one end and this end is free. Now when you pull up, what happens? When you stretch it in this side, what happens? You can see rarefactions that is shown by the R in your figure. And when you push it back, so it come closer to each other, it will be compression. So that means this kind of thing is what kind of motion? It is the longitudinal motion. Longitudinal wave is forming. Now by doing this, still you can hear some voice. Very slight voice is there, but due to this vibration kind of thing, you can hear the voice. This voice is nothing but the sound wave is generating from this. Understand? So now what is meant by why I am taking this example of a spring here? Just to explain you that sound can be generated by this to and fro motion. This is a generation of sound wave on a spring. The question will be like how the sound waves are generated on a spring. So it is due to the compression and rarefaction. Now, whenever you are explaining the generation of sound wave on a spring, so the most important points are compression and rarefaction. Underline compression and rarefaction.
Okay.
Now, next second subheading will be sound waves. First is wave on a spring. Next subheading sound wave. A sound wave, comma, produced for a sound wave produced for example, a sound wave produced for example by a loudspeaker, comma, consists of a train, consists of a train of compressions, consists for a train of compressions and rarefactions, consist of a train of a compression and rarefaction in the air, in the air, in the air. Change the paragraph. The speaker has a cone which is made to the speaker has a cone which is made to vibrate, in and out, which is made to vibrate in and out by an electric current, by an electric current, full stop. When the cone moves out, when the cone moves out, comma, the air in front, is compressed, the air in front is compressed, comma, when it moves in, when it moves in the air is rarefied. In bracket, see the spelling in screen. Rarefied. In bracket, write down goes thinner. Goes thinner. The wave progresses through the air. So stop. The wave progresses through the air, but the air does not move. But the air does not move as a whole. But the air does not move as a whole. So stop. The air particle vibrate. The air particle vibrate backwards and forwards. The air particle vibrate backward and forward a little, backward and forward a little as the wave passes. As the wave passes. When the wave enters, when the waves enter, your ear, when the wave enter your ear, when the wave enter your ear, the compression and rarefaction, cause small, rapid pressure changes, rapid pressure changes on the eardrum. Rapid pressure changes on the eardrum, and you experience the sensation of sound. Change the paragraph. Number of compressions produced. The number of compressions produced per second. Number of compression produced per second is the frequency of sound wave. In bracket f, small f, and is equal to the frequency of vibrating loudspeaker. Frequency of vibrating loudspeaker. Vibrating loudspeaker cone. Comma.
With a phone or?
Frequency of the vibrating loudspeaker cone. CONE, cone.
Oh, cone, okay.
Comma. The distance between successive compressions is the wavelength lambda The distance between successive compression is the wavelength lambda. As with transverse wave, the speed equals to, as with transverse wave, speed b equals to f lambda. Now again I'm sending you a picture, you have to draw. Got the picture?
I'm opening it now. It's loading. Yes, got it.
Okay, draw it, and once you're done, let me know.
I'm done.
Okay, so basically here what is we have written that how the sound is produced in the speaker. Now in loudspeaker, have you seen some loudspeaker or some microphone mic? So what happened in that? It has a cone. Inside that, it has a cone-like structure. Now what happened in that cone? That there will be complete compression and rarefaction. Continuously there will be compression and rarefaction. So that due to that compression and rarefaction, there will be the generation of sound. Now suppose this is the loudspeaker. From here you are speaking something. Okay, so that means the voice is entering from here. Now what is the use of loudspeaker? It enlarge, it increase the amplitude. It will create a much louder voice. That is what loudspeaker is. But when you speak very feeble voice, it just it increase the amplitude, it do the amplification process, and it increase the sound. That is what the loudspeaker is doing basically. Now what happened in it? There is a cone inside it with in which there is a complete train of compression and rarefaction. The meaning is whenever Just like in the starting, I told you that there is a vibration. Wherever there is a vibration, there will be generation of sound. So now deep inside that vibration means what? Compression and rarefaction. Whenever there is a train of compression and rarefaction, the sound will be generated. What is compression and rarefaction? Just now I have explained. Now here in this example, what is happening?
You want me to explain it?
Yes.
Okay, basically from the smaller end of the cone, you're putting in a vibration. It could be your voice or a string or whatever. As long as it's a vibration, it will create sound. And throughout the cone, it will amplify the amplitude, making the sound louder.
Now see, when the cone move out, now what happened? See here what is happening. There, wherever we place the loudspeaker or the microphone, where whatever, there will be air around it. The medium will be what? Air. So whenever there is a, when we speak something, so what happened? The cone moves out. Suppose we are speaking from the arrow side. So what happened? The cone inside it. Suppose it is like this. So this cone moves out. It comes like here. So when it comes out, so air here outside this loudspeaker. What happened to this air? This air got in front of this loudspeaker got compressed. We speak from here, cone moves out, air got compressed. Clear?
Here.
Now, when it comes back, sorry?
Can you explain it one more time?
Okay. Whenever, what I'm saying, suppose this is a microphone. Inside it, it is a cone-like structure. When we speak something from here, the cone moves out. It's like a movable thing, so it tends to come out. Now, when it tends to come out, so air surrounding this loudspeaker is compressed. It got compressed. Okay? Because this cone is making pressure in air. So it got compressed. On the vice versa, when it comes back, when it comes in, when the cone comes in, the air is rarefied. Rarefied means it will be like this. It is the rarefaction is happening. That means the air becomes thinner. And this is how the wave progresses. Okay, although the air is not moving, but the wave, the sound wave entering from here is moving. How it is moving? Because of the compression and rarefaction that is getting produced. Clear? And we know that wherever there is a compression and rarefaction, that means there will be wave generated. Now here the wave is transmitted because of the motion of the cone inside the loudspeaker. Clear?
Clear.
Now the question is whether the air as a whole is moving or just the wave is moving.
It's just the wave that's moving.
Yes, air is just producing the compression and rarefaction. It is not moving at all. It is just helping the wave to move further and to become a progressive wave. Clear? Now in that diagram, whatever you have made, in that we have marked lambda. Now what is lambda? So distance between the two consecutive compression, always we consider compression. We don't consider rarefaction. We can consider it that rarefaction also. If we don't have the value for compression, we can take the rarefaction also. But in general terms, we take the compression. So distance between two consecutive compression will be your lambda, that is the wavelength, and frequency will be how much number of compression produced in 1 second. Per second, how much compression is producing is the frequency. Now here also the same equation is followed, that V equals to F lambda, that we have understand for the general wave. It is considered for both transverse as well as longitudinal. So here also the formula remains same. Okay. Now just go through whatever you have written and then come back to me and then you only explain it.
All of it?
No, just this this thing, this topic. Sound waves.